Okay, hello everyone. This is Brian again. I'm gonna try and solve 7.6, but I had a little bit of a problem with it, but maybe someone can help me with a comment. So part A says determine the principal values and principal directions of f, and it gives you f, which is that matrix right here. So the first thing I did was to change it to f minus I lambda. So all I did was add minus lambda to the diagonals. Um, the next part, to get our eigenvalues, we take the determinant of that new matrix. So that determinant is equal to this right here. Expanding this out, you get a whole lot of terms to combine, but this is just simple algebra now. If you pretend lambda is an x, you can then eventually get this equation down here, and you set it to zero to find the solution values for lambda. So lambda 1 we get after solving this here, we get lambda 1 is equal to 13. Lambda could also equal 7, and lambda could also equal 3. And all those three lambdas satisfy that equation. So now that we have our eigenvalues, we need to find our eigenvectors. My camera focus a little bit. So to find those, we plug lambda into f minus I lambda times mu. I guess this could be a j, this could be a k down here. Regardless, for the first one, we're just going to subtract the diagonals from lambda 1, which is 13. After that, we then get these equations here doing if we well, I suppose I should have wrote out the block of mu's. So we'll just do that real quick. Mu I, not I, mu Roman numeral. Roman numeral 1 and I are too similar for my taste. Okay, Roman numeral 2. No, not 2. Shoot. That is going to be a 1. Roman numeral 1 sub 2 mu Roman numeral. Oh, I'm doing it again. Roman numeral 1 sub 3. Okay, and we want to find this vector, which is going to be mu superscript 1. And I guess we'll just write this out. It's here is f minus I lambda. Okay, so to find our eigenvectors, we need to find the value for mu1, mu2, and mu3. So first things first, we just expand this equation out. So this times that plus that times that plus zero times etc. And we get these three equations. From these three equations, it's quite obvious that mu sub 3 is going to be 0 because when we set it to 0, um, 0, 0, -5, there's only -5 there. It could be, well, I guess it could be, no, it only can be 0. There's no other value. So then we have to solve these two equations for mu sub 1 and mu sub 2, which I did. You get 2 over the square root of 5 and 1 over the square root of 5, giving us our final vector mu1 equals 2 square root 5 u e vector e1 plus 1 over square root of 5 vector e2. And that's our first eigenvector. So we do it again for the rest of our lambdas. So here you can see I had lambda equals 7, and I plugged it into here, got my equations out. Um, so here we get some 0 plus 0 plus 0 is equal to 0. That sort of confuses me. I think that means that mu sub 3 is equal to 0. But I noticed that other people posting their solutions have set it equal to 1. So if anyone knows why that is, just leave me a comment. I could use a little clarification. So anyway, the only solution for the two equations here, though, is that mu sub 1 and mu sub 2 must also equal 0. So our eigenvector for this is 0, 0, 0. Finally, we go on to our last lambda. Lambda equals 3. So we have um a new matrix now. It's 840, 420, 004, etc. And we do it again. So immediately I can see that mu sub 3 must be 0 again. Setting up these two equations, we can solve for mu1 and mu2, which turn out to be 1 over square root of 5. Mu2 is 2 over square root of 5, giving us our third eigenvector, that is E1 over square root of 5 plus 2E2 over square root of 5. And that's its direction, its unit direction. Um, as for part B, I'm not sure if I did this quite right, but I gave it a good shot. So we want to create a new matrix A. I chose A because A is always rotation. And we want to, for this matrix, we want to put the eigenvectors as columns and use it for rotation onto for going from F to F prime. And it should show that there's a diagonal form at the end. So from equation 6.11, we get F equals A transpose F, sorry, we get F prime equals A transpose dot F dot A. I should make this prime a little more bold. Ignore the giant scribbled out part at the top. So here I started to watch videos of the other solutions on the board, and I noticed that there was a 1 in their second principal eigenvector for u sub 3. Once again, I'm not quite sure why, but I substituted it in, and it gave me the correct answer. So I will just take that as it is and look into it later. But once you solve this up here, you do get the diagonal down here. And I hope that makes sense. Thank you for watching all the way to the end.